All right, okay. So again, I'll be talking about controlling open quantum systems. And this is a joint work between two groups at two universities. One is Penn State, and the other one is Peking University. Now, two of the graduate students are here at the conference. All right, and at Penn State, this is kind of a joint force between a math department and the computer science department. All right. So in quantum optimal control, what we do is instead of letting a quantum system evolve by itself, we try to control by applying external fields and to control what the system does. Now, this problem is not new. It comes up in quite a few applications. So you could be thinking about maximizing certain physical properties, like controlling electron current through a quantum device. You could also be thinking about opening and closing a chemical bond and then turn it into a storage device. And of course, the application to quantum computing devices is obvious. Now, my talk is going to be focusing on the simulation aspect, right? And because of the control aspect, you have to simulate the dynamics many, many times. And what also complicates the problem is that when you look at the landscape of this problem, it's highly non-convex. And so because of that, you're going to have to do many, many quantum simulations. All right? And so it's important to make this part efficient. Now, I'm going to be focusing on three specific questions. The first part is that we are actually controlling a system that's constantly interacting with an environment. So I'll talk about how to simulate this kind of dynamics. And eventually, this comes down to simulating the Lindblad dynamics with a time-dependent Lindblading. Right? Now, the second part of this is a classical optimization algorithm. And so I'll talk about the optimizers that we are using and how to interface these two components. And toward the end, I'll summarize the overall simulation complexity. All right, now to look at a specific scenario, we're going to look at an open quantum system in the Markovian regime. And in this regime, a universal description is the Lindblad equation. And so what you're looking at here is the dynamics of the density operator. Now, if you look at just the first part of this, this is nothing but the von Neumann equation. All right, and what this uj of t is it represents a control variable. So you can think of the mu j as a dipole operator. Now, these remaining terms are representing the interactions within the environment. And the reason that this is so simple, right, is because of the fact that we are in the Markovian regime. And we can easily write down this closed form of the equation. Now, because of the control part, this Lindblad operator is actually time dependent. So the first thing that we have to think about is how to simulate this efficiently. Now, but in the end, we want to be able to tune the control variables here so that certain functions are optimized. For example, we could try to maximize this expectation, right? So the rho of t is the density operator at time t. The second term here represents a regularization term, and mathematically, it gives you a bit of convexity. Now, there are other choices. So you could be trying to drive the system to a specific quantum state, right? Now, what is a little bit disappointing in this business is that for closed quantum systems, typically they are controllable if you have enough terms in here in the control part. But for open quantum systems, it is known that the system is not controllable. So we cannot drive any arbitrary state to a target state, right? So because of that, we're just going to settle this as an optimization problem, and we try to maximize this quantity the best that we can. Right? So that's kind of the setup of the problem. Now, let me try to answer the 3 questions that I posed at the beginning. So the first thing is, like, how do we simulate this Lindblad dynamics efficiently? Fortunately, in the last few years, there are several algorithms that were developed, and they are all very efficient. So here, we're going to use an algorithm that we developed previously for time-independent Lindbladians, and it is based on a cross-form representation of the quantum channel. So essentially, the dynamics of the Lindblad equation forms a quantum channel, and so we're going to represent that channel in the cross form. Okay? And here's the basic idea. So you're going to divide the terms on the right-hand side into 2 groups, and this is the first group here, and so it has the commutator and the anti-commutator term, right? So this part of the dynamics can be represented through a matrix exponential where the matrix involves these, right? And then the second part is this right here. This came from the noise from the environment, right? Now, what's nice about this part is that this is already in the Krauss form, okay? And then to actually piece them together, you use the Duhamel's principle. You use the first term as the main sort of driving term, and then you write down this integral form of the solution. And then in the integral form, you can apply the Duhamel's formula again and just replace this rho of t by this term here. And so that'll leave you with an error that scales like t squared. All right, what is appealing about this formula is that, as I mentioned before, if you look at this term here, this is nothing but a matrix multiplying rho from the left and another matrix multiplying rho from the right. And so that's automatically in the Krauss form. And then this part, this Lj part, is also in the Krauss form. So if you put everything together, you can write it as a Krauss form of the quantum channel. Now, nothing is going to stop you from continuing with this formula, right? So you take this rho and then plug it in, and you can try to extend this many, many times. So essentially, as I mentioned before, both of those 2 terms will produce an expression in the Krauss form. Of course, a composition of 2 Krauss forms is another Krauss form. Now, for the integrals, it doesn't matter how you approximate them. It still stays as a Krauss form. All right. Now, eventually, when you extend this far enough, you can achieve any arbitrary order of accuracy, right? So in the end, the problem comes down to implementing a Krauss form, right? Now, we just simply use the LCU type of idea, and to do that efficiently. Now, to put everything together, the algorithm is going to scale with, sort of with respect to time, like this, and also depends on the norm of this Lindbladian. But in terms of epsilon or the dimension, it's logarithmic. Okay. Now, you can improve these. So, we learned a lot about the Hamiltonian simulation techniques. And so you can also do the interaction picture technique. So if you have part of the Hamiltonian that has much larger coefficient, but much easier to simulate, then you can borrow the ideas from the interaction pictures and do the same. And this is in our paper. And you can also try to improve the dependence on the norm of L by rescaling time, and so that eventually you also have this L1 norm scaling result. Right. So that's the first question. So this is how we simulate the Lindbladian. Right? Now, the second component is the optimization. So how do we compute the cost function? How do we compute its gradient? Right? Now, we use the gradient-based algorithm because for these algorithms, the complexity of the optimization algorithms are much easier to figure out. All right. Now, to compute the gradient, we use the quantum gradient estimation algorithm. So we follow this paper, and so this is an improved method on the Jordan's algorithm. All right. Now, to make this work for this particular problem, you first have to show that so you first have to show certain smoothness of the objective function, and it turns out that luckily for the quantum optimal control problem, you can show that this J of U belongs to the Gavry class, so you do have the smoothness. And then to make this work, we also have to discretize this in time, because this U originally is just some continuous function, so it's in an infinitely dimensional space. So we can introduce a time discretization so that this is a finite dimensional problem, right? And to also make this work, we need to kind of express this as an expectation. And so this follows from the Lindblad simulation, where eventually we get a purification of the density operator. So the objective function that we want to compute is expressed as an expectation. All right. And of course, the gradient is going to be we compute all its components. So this algorithm relies on another algorithm, which is about estimating multiple observables. Okay. And to use this algorithm, we need a phase oracle, which can be converted from a probability oracle. Okay. So let me just tell you how this algorithm scales. Right? So let's say that this is the gradient that we want to estimate, and what this algorithm produces is an estimator of the gradient with high probability. Right? The dependence on the number of components here, number of the variables here, which is proportional to the time duration, is linear. And this is because we are actually using the L2 norm, right? And so in the original paper, this dependence is like square root of t. But the issue here is that in analyzing the convergence of the optimization algorithms, we usually use 2 norm, right? And so there's a little bit of a gap there. So we didn't take full advantage of the efficiency of the gradient estimation algorithm. But that's what we have to settle with at this point. All right. So now we have 2 pieces ready. So let's see how we can kind of combine them. Now, the most obvious choice when it comes to the optimization is the gradient descent algorithm, right? And so in this particular problem, it's going to be the gradient ascent, because we are maximizing an objective function, right? Now, typically, this algorithm is guaranteed to converge to a stationary point, but it may get stuck at other, let's say a saddle point or local minimum, all right? Now, if you're lucky and you're very close to the actual solution, then this algorithm can have linear convergence, so the dependence on epsilon is only logarithmic. And that's very nice, but usually we're not that lucky. So we have to think about the global convergence. All right, and so one way to stay away from those undesired stationary points is to use perturbed gradient descent. So we're borrowing these ideas from machine learning algorithms. All right, so this is a very simple modification of the gradient descent algorithm, where you actually, at each step, you add some stochastic perturbations. All right? And so what happens is that if the gradient can be estimated with a variance that's proportional to epsilon squared, and of course, this is the typical condition on the learning rate, then this algorithm can converge to a stationary point that satisfies an approximate first and second order optimality condition. So your gradient is going to be close to epsilon, and your Hessian is going to be bigger than negative epsilon, square root of epsilon, right? And so the complexity scales like 1 over epsilon squared in terms of the tolerance parameter. Okay. Now, we also thought about another variant of this method. This is a bit like the momentum method, right? And this, in the machine learning community, this is called accelerated gradient descent, right? Now, so this is based on the momentum method, but then you introduce some Gaussian perturbations when you feel like you're getting stuck. And you also want to introduce a negative curvature condition and to further explore, right? Now, this method gives you a slightly better dependence on epsilon, right? So you make all these modifications, and in the end, the improvement in terms of epsilon is like epsilon to the 1/4, right? Okay, so now let's see how we combine them, right? All right, so so if you're just interested in fulfilling the first order condition, meaning that the gradient is less than epsilon, then the analysis is very straightforward, right? So the complexity is basically like this. I threw away all the logarithmic factors, right? So the NC here, I forgot to mention what it is at the beginning. This NC is the number of control variables. So the number of U or the number of mu's. T is the time duration, and the L is the norm of the Lindbladian. And the dependence on epsilon is a bit like a bit less than epsilon cubed. All right. So what the reason that we like this sort of problem is that we have a bunch of choices for the Lindblad operator, Lindblad simulation algorithms, and we also have quite a few choices for the optimization algorithm. And so we kind of have to see how they interface and how they can be combined. And so what happens is that when we want to incorporate both the first order and the second order condition, the analysis becomes much more difficult. And so at this point, the best that we can get is this epsilon to the power 5 dependence. So this is a lot higher than this scenario. Okay? And the reason for this is that in the gradient estimate, in order to make sure that the proof goes through, in the gradient estimation algorithm, we have to make the estimation much, much more accurate. So having epsilon tolerance is not enough. Okay. Now, let me do a summary. I think I can finish on time. So my talk discussed several aspects in the optimal control of the open quantum systems. So I talked about how to simulate the Lindblad dynamics. So this part does not contribute a lot to the overall complexity in terms of epsilon. So you can definitely make other choices. Now, we used the gradient estimation algorithm. And so the overall complexity considered first and second order optimality conditions. So the remaining challenges is that we should have a better understanding of the overall landscape to get a better, to develop better algorithms, to get better complexity results. So we know how to, right now we know how to control open quantum systems in the non-Markovian regime. I don't know how to implement this on near-term devices. Okay? With those remarks, I'm going to stop here, and thank you for your time.
So any questions?
Great. Thank you for the talk. I had a question, I guess, about the typical behavior of the control parameters.
Right. Mm-hmm.
Should I sort of expect that as you look at the trajectory, say, of one of them through time,
mm-hmm.
is it going to be really messy, or do they sort of look predictable for like a nice physically motivated problem?
It's a relatively smooth. It's actually a relatively smooth profile. It's not going to like have like very sharp changes. At least that's what we saw in some of the numerical experiments.
Okay, cool. Thank you.
Yep.
Any more questions? Well, I guess everyone's hungry. So yeah, thanks again for all the speakers in this morning session, and yeah,